So our next talk in the session is atomic scale simulation of lunar water retention induced by space weathering. The authors are Huang, Nomura, and Wang, and the speaker is Ziyu Huang. You share your screen.
All right, can anybody see my screen?
It looks good. Looks a little small, but I think it's all right.
Let me retry it. Let me reshare it again. How about now?
I think that'll do it. It looks like it's full screen,
Okay.
not presentation.
Okay, thanks. All right. Good morning or good afternoon. I'm Ziyu Huang from University of Southern California, and I work with Professor Joseph Wang. This work is also collaborated with Professor Kenichi Nomura and Professor Aicho Nakano. This talk is about atomic scale simulation of lunar water retention induced by space weathering, and I will introduce some updates on implementing molecular dynamics simulation to planetary science problem. Well, there are many space weathering processes like solar implantation, micrometer impact, or deep dielectric charging, which can lead to dielectric breakdown. We want to start from a problem that is strongly related to those processes, which is the lunar water cycle. And there are multiple sources for lunar water, and in this talk, we focus on solar-related sources. Solar implantation provides hydrogen to the lunar surface, but since the temperature is not high enough for water formation, it requires additional energy. Well, micrometeor impact and dielectric breakdown could possibly provide enough energy, but it could also provide too much energy that can make the surface lose water. So in this way, we use atomic scale simulation to see if we can evaluate the contribution of those of each process. The model we use is ReaxFF force field coupled with molecular dynamic simulation, and also a polarizable charge equilibration model. The advantages of this potential are, for instance, it can directly simulate chemical reactions by bond forming and also bond breaking. And it can also capture the atomic structure of the regulus, like crystal structure or amorphous polar structure. So first, we introduce solar implantation and sputtering. We'll limit the case to PSR since there's no photo disruption and the temperature is low, so that the thermal disruption is low as well. The horizontal velocity is drifting velocity of solar wind, which is about 400 kilometers per second. And the vertical velocity is calculated by the plasma sheath theory, which is the ion crystal velocity square root of electron temperature over the mass of protons. And the value is about like 40 kilometers per second. And after each implantation, we relate the surface to the original temperature, which is about 100 Kelvin, making sure there's no energy residue before the next implantation cycle. The blue particles are hydrogen, and we continue to implant more hydrogen atoms. So as number grows, we can see like more and more particles are reflected. Well, this reflection of solar wind is consistent with observation by Kaguya and also Chandrayaan-1, but it's not a focus today. And after we implanted about like 3,000 hydrogen atoms, we can see the surface is almost covered by hydrogen atoms. And there are even some water molecules that are sputtered from the surface being injected. And then we use group analysis to identify each molecules and chemical groups. And the left two figures are the number of hydroxyl group, hydrogen molecules, and also water molecules. The upper one is above the surface, and the other one is on beneath the surface. Well, the data shows that most of the hydrogen atoms from solar wind are turning to hydroxyl groups and also hydrogen molecules, H2. Water molecules are also detected, but there are very few of them. When we convert it to a 60 micrometer dust, the OH and H2O abundance is less than 1 ppm. But it shows that incoming solar wind hydrogen atoms can combine with hydroxyl and then form water molecules, although it's very unstable and easily to be sputtered. Another interesting thing we found is that although the hydrogen molecules H2 number is still growing, the number of hydroxyl and also water molecules are becoming stable. So this indicates that the surface will be saturated with hydroxyl and water molecules if the implantation continues to go on. And the saturation time we found is about 400 days based on the solar wind conditions and local temperature. And then we move on to micrometer impact. We keep the implanted samples from previous simulation and then replicate it in X and Y direction by 4 and 4. Then we place a nano-phase silica sphere on the top and then assign an impact velocity to it. The snapshot showing the bottom, we created the surface by alpha shape method, and we can see the mini crater formation as well as some molecules and atoms being ejected from the surface. We tested 4 different velocities ranging from 8 km per second to 20 km per second. The velocity are all perpendicular to the surface. We will definitely include the effect of impact angle in the future. The left figure is the total water molecules, and on the top right is the number of water molecules above the surface, and the bottom right is for those on or beneath the surface. And we found that in total, micrometer impact always produce more water by providing energy to hydroxyl group for recombinated absorption. But at the same time, if you look at figure C over here, the retention of water molecules at impact site is strongly related to the velocity. So for 8 km per second, if you can see, the abundance of water molecules almost go back to the original abundance. But for 20 km per second, the impact almost double the water abundance. And for those above the surface, they're being classified as molecules ejected from the surface. And almost 50% of them escape from the moon, and 50% of them contribute to the exosphere, or they are redistributed to the ground. And when we look at the impact side, we found that the post-impact side is becoming amorphous and also porous. The figure on the right shows the silicon oxygen 4 tetrahedra, and it shows a significant change of the surface atomic structure. The impact removed the hydrogen on the surface, making the surface fresh again, and this could be ready for another implantation cycle. And also the amorphous structure make it possible to deposit more hydrogen atoms in the implantation, and thus more water molecules could be formed when the second impact occurs in this post-impact site. Regarding dielectric breakdown, for the interest of time, I will refer the formation of water molecule to the last ESF talk. This is a QR code, and also a recent GR paper we published. What we want to update this year is that the electric field can also trigger desorption, which is a loss mechanism. And compared to dielectric breakdown, the desorption starts at a lower electric field level. This can be seen on the right. When applied an electric field about like 10 to the order of fifth voltage per meter, the number of molecules in total stayed relatively stable, meaning that the electric field won't break H2 or H2O. But the hydrogen molecules and also water molecules are leaving the surface. That can be seen from the lower 2 figures. And in contrast to thermal desorption, this occurs more frequently in colder region. And originally we thought that like cold region, especially PSRs, are very quiet and everything stay as it is. But the deep dielectric charging theory shows that there could be some loss mechanism just because the surface is too cold. And here we put a table as a summary listing each space weathering process and the mechanism of water formation and loss, and also the area effect. The implantation and micrometer are almost everywhere, but there's different conditions, like the solar wind velocity and implantation angle. Well, dielectric breakdown occurs mostly in colder regions. And currently, we can conclude that within PSRs, the combination of implantation and micrometer impact can continuously accumulate water molecules and garden them into a deeper depth. And there are some periodic feature of the combination to the contribution of water molecules. And future work will definitely include the total contribution of those space weathering effect and also model the global lunar water distribution based on the atomic scale simulation. All right, with that, I will take any question you may have. Thank you.
Sorry, I've got a timer going, but we have a quick 1 minute for anyone who has a quick question for Ziyu.
There is a question in the chat by Papati. She says, excellent talk. This is really interesting and important work. Have you tried any direct comparisons of simulation results to experimental results? The simulation seem mature enough that you could potentially do that, which is great.
Oh, thanks for the question. Yeah, we're trying to, actually we're trying to implement the experimental dielectric breakdown in our lab. And also we're trying to find some experiment data for the micrometer to be compared to the MD simulation. And this is definitely our future work, but currently I don't have any updates for that.